Greetings, I'm Kadir Musayamac. Welcome to my project presentation. As a part of my yearly 402 graduation project and under the supervision of Professor Fezarikan, I have completed my project titled Investigation of Geophysical Signal Variability using the Fourier transform. The periodogram is a signal processing tool first used in the analysis of stationary time series to estimate their power spectral density. It is particularly capable of estimating the PSD of intermittent or irregular signals where the traditional Fourier transform methods might not be adequate. The periodogram is computed by taking the Fourier transform of the autocorrelation function of a given signal. This method leverages the Wiener-Khinchin theorem, which states that the PSD of a stationary random process is the Fourier transform of its autocorrelation function. Periodogram function in MATLAB that computes the periodogram for any given signal without any control on the parameters of the input signal that needs to be optimized. It is also incapable of dealing with intermittent signals on its own. In this project, a user-friendly algorithm is designed to compute the periodogram, optimizing the output with respect to signal length, sampling frequency, and not a number of values. The autocorrelation is the cross-correlation of a signal with itself. The autocorrelation measures how similar the signal to a delayed copy of itself for each amount of delay. It has applications in finding repeating patterns or recognizing the fundamental frequency in any given signal affected by other harmonic series. The periodogram is computed by taking the Fourier transform of the autocorrelation function of a signal. The algorithm for autocorrelation will begin by taking two input arguments, signal and the maximum number of lag, converts the input data to a double precision and calculates its length, mean, and variance, initializes the variable and loops through the lag values and computes the autocorrelation coefficients. Algorithm for periodogram will begin with removing not a number values from the input vector, calculating size of the input vector after removing the not a number values, computing the autocorrelation of the input signal, computing the fast Fourier transform of the autocorrelation, and lastly computing the periodogram magnitudes. Analysis of geophysical signals are achieved through the use of periodogram algorithm. Here as a demonstration I have used a dataset of sunspot numbers spanning from January 1, 1988 to January 1, 2021, covering 33 years and equivalent to 3 solar cycles has been collected. These are daily averaged values. Here is the periodogram output in frequency. The periodogram output for sunspot numbers have peaks in the given frequencies. Converting them to the periods will give us 22.3 years, 11.4 years, 5.4 years, and 33.3 days. Same tests have been done on KP index as well. Again, we have a dataset of daily average values spanning from January 1, 1988 to January 1, 2021. Again, using the outputs of the periodogram algorithm for KP index, we are computing the periods. Here are the found periods: 18 days, 29 days, 8,333 days, 4,166 days. To assess the accuracy of the input data, the normalized mean square error was calculated for each set of input vectors, which are space-vector indices. These indices are sunspot numbers, DST index, KP index, alignment alpha index, and AE index. The normalized mean squared error values for each input vector is summarized in the table below, and our average normalized mean square error is 0.48% error. In conclusion, in this project, an algorithm was developed to evaluate the periodogram of cosmic radiation signals designed to handle intermittent input data efficiently. The computational load for this algorithm is similar to that of the built-in function, and the maximum data size can be processed depends on the hardware that is used. Throughout this project, several key observations were made. The modular structure of the algorithm provided a flexible design, as it allowed the ease of adjustments and testing each part separately. However, during the testing, small oscillations around the true frequencies were observed, requiring additional refinement to identify local peaks within a specific range. This issue was successfully addressed by narrowing the detection window, which improved the precision of the frequency extraction. Thank you for watching this video.